Morning everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to continue to look at derivatives in the context of real-world problems. So we're going to look at two application problems and look at what the first and second derivative mean in relation to the original function. All right, so it says we have done a lot of work to understand and apply different strategies in finding derivatives. However, we have not spent a lot of time talking about what derivatives mean in terms of real-world scenarios. This unit will focus on that. So just like our little introductory lesson in the previous video, we talked about particle motion. We had an introduction to position, velocity, and acceleration, and which ones were the derivatives, which ones were the original functions. We're going to continue to work on that today, and we're also going to look at a different type of application problem, one that's not specifically particle motion, but one where we can look at the relationship between the original function and its derivative. So it says, suppose that the amount of water in a holding tank at t minutes is given by the function v of t equals 2t squared minus 16t plus 35, and we need to determine each of the following. Part A, is the volume of the water increasing or decreasing at t equals 1, and we need to justify our answer. So the original function that they give us, right, is the volume function, and we need to determine whether that function is increasing or decreasing when t is equal to 1. Well, I'd encourage you to pause the video, and I actually encourage you to pause the video and work through as many of these problems as you can get to, or maybe do them one by one and come back to the video and see if your intuition's correct. But we've actually covered the material necessary to answer this problem, right? How do we figure out whether an original function is increasing or decreasing? Well, we have to look at that derivative and see whether it's positive or negative. So first thing I need to do is take the derivative. So I get v prime of t is equal to 4t minus 16. And it gives us a value that we need to evaluate the derivative at. So v prime of 1 is going to be equal to 4 times 1 minus 16, which is equal to negative 12. So if the first derivative is negative, that means the original function is decreasing. So we can say volume is decreasing at t equals 1 because v prime of 1 is negative, or we can say v prime of 1 is less than 0. Let's make this look a little better. All right, moving on to part B. It says, is the volume of the water increasing or decreasing at t equals 5? Justify your answer. Well, we've already found the first derivative, so we're just going to substitute in 5 this time for t. So I get v prime of 5 gives us 4 times 5 minus 16, and that gives us positive 4. So we would say volume is increasing. At t equals 5 because v prime of 5 is greater than 0. Now, it is important in both of these that you don't just say the volume is increasing or decreasing, right? They're asking us about a specific point in time. So you need to say the volume is decreasing at t equals 1, or the volume is increasing at t equals 5. And then this justification is required. It's necessary. You would not earn full points on a free response question if you did not include that justification. All right, let's move on to C. It says, is the volume of water increasing faster at t equals 7 or t equals 5? Justify your answer. Well, I already know what the rate of change in the volume is at t equals 5, right? We know it's 4. We don't have any, it doesn't give us a units for the volume, so we could just say 4 units per minute, because it does give us a unit for t. So what I need to do is I just need to find the rate of increase at t equals 7. I'm just going to scroll up here for us. So v prime of 7 is going to be equal to 4 times 7 minus 16, which gives me 28 minus 16, which gives me 12. Again, I already knew that, right, v prime of 5 was equal to 4. So they're both positive. The volume is increasing at both t equals 5 and t equals 7, but the rate at which it's increasing is higher at t equals 7 because 12 is greater than 4. Right? Even though we don't know what the units are for the volume, whether it's gallons, whether it's cubic meters, whether it's millimeters, regardless, 12 of those units is going to be greater than 4 of those units. So we would say increasing faster at t equals 7 because v prime of 7 is greater than v prime of 5. And again, you would need this last little piece of the justification to earn full credit. All right, part D, is the volume of the water in the tank ever not changing? I.e., when, if at any time, is the volume of the water staying the same? Well, we could think about just a regular function, right? If we were thinking, is a function ever not increasing or decreasing? Well, we would need to be looking for something about the derivative, right? If the derivative is positive, the function's increasing. If the derivative is negative, the function's decreasing. If the derivative is 0, well, that's one spot where the function is neither increasing nor decreasing, as well as if the derivative is undefined. That could also be a spot where the function is neither increasing nor decreasing. Now, our derivative, the general derivative here, v prime of t, we said was equal to 4t minus 16. This is never going to be undefined because it's continuous over its entire domain. So we only have to check for where it's going to equal 0. So we set the derivative equal to 0 because that would be a spot where the original function's neither increasing nor decreasing. And we're just going to solve for t. So I get t is equal to 4. So we would say the volume of water is not changing at t equals 4 because v prime of 4 is equal to 0. And that would finish this part off for us. All right, let's go on to the second page, and let's look at a particle motion problem. Again, I'd encourage you to pause the video, attempt this problem on your own before you come back and look at the solutions. So it says, suppose that the position of an object after t hours is given by the function g of t equals t divided by the quantity t plus 1. And we have several questions. Part A says, what is the particle's position at t equals 5? Justify your answer. Well, we're given the position function, right? That is our g of t. So all we should do is substitute in 5 for t. So g of 5 is equal to 5 over 5 plus 1, which gives us 5 over 6. And it does not give us, again, it doesn't give us units here. It doesn't tell us, meters or centimeters or miles, etc. So we do not have to include units with our answer. And this work would count for our justification, right? Because we've shown what we're doing. We've shown that g of 5 is equal to 5, 6. B, is the particle moving in the positive or negative direction at t equals 5? Justify your answer. So we have to think, do I need to look at the original function, right? If I substitute in a value in my original function, that's going to give me the position. But it's not going to tell me whether the particle is moving, you could think of it as forward or backwards or left or right. Here they say positive or negative. So position doesn't tell me which way the particle is moving. I have to look at my velocity for that. And velocity, we know, is the derivative of the position function. So I'm going to take the derivative of my position function, g prime of t. We have to use a quotient rule here. So I take the derivative of my numerator, which is 1, times my denominator, t plus 1, minus my numerator, which is t, times the derivative of my denominator, which is 1, all over my denominator squared. If I do some simplifying, you're going to get t plus 1 minus t. These t's and pluses may be a little confusing, so we have to sort those out. All over t plus 1 quantity squared, which gives me 1 over t plus 1 quantity squared. So right here, this is our general derivative. We need to figure out what the derivative is equal to when t is equal to 5. So g prime of 5 is equal to, oops, nope, I did make a mistake there. 1 over 5 plus 1 quantity squared, which gives me 1 over 36. So if our derivative is positive, then that means our original function is increasing, which means we'd be moving in the positive direction. So particle is moving in the positive direction at t equals 5. Don't forget that part, at t equals 5, because g prime of 5 is greater than 0. Okay, so that would be a complete justification. All right, let's go ahead and look at part C. I'm going to erase this for us. Scroll down. 2 questions left. It says, is the particle's velocity increasing or decreasing at t equals 5? And we need to justify our answer. So for part B, we were asked, is the particle's position essentially increasing or decreasing? Was the particle moving in the positive or negative direction? Now we're being asked, is the velocity increasing? So if I want to figure out whether the first derivative is increasing or decreasing, I need to look at whether the second derivative is positive or negative. So my first derivative, g prime of t, that was equal to 1 over the quantity t plus 1 squared. So if I want to find g double prime, which would be my acceleration function, derivative of my numerator is 0, so it doesn't matter what my denominator is, minus my numerator times the derivative of my denominator. So here I get 2 times the quantity t plus 1 to the first power, times the derivative of my inside, which is just 1. So it's not too bad of a chain rule there. All over my denominator squared, so I get t plus 1, that quantity to the 4th. If I do some simplifying, I guess I'll do 2 more steps. I'll get negative 1, and then I have 2t plus 2 all over t plus 1, that quantity to the 4th power. And then I get g double prime of t is equal to negative 2t minus 2 all over the quantity t plus 1 to the 4th power. And now I need to figure out, is the second derivative positive or negative when t is equal to 5? So I just need to substitute in t, substitute in 5 for t. I'm going to come back up here. So g double prime of 5 is equal to negative 2 times 5 minus 2 all over quantity 5 plus 1 to the 4th power. We're going to get some larger numbers here because 6 to the 4th is a bit bigger. So I get negative 12 all over 1,296. And I don't need to worry about simplifying because I really just care about the sign, right? So second derivative is negative, which means the particle's velocity is decreasing. At t equals 5, because g double prime of 5 is less than 0. So for this one, we had to find the second derivative and use that to justify. All right, and let's finish off by answering part D. It says, is the particle ever stationary? Justify your answer. Well, if the particle is stationary, that means we need to look for where the derivative is equal to 0. So where the velocity is equal to 0. And we could also explore where the velocity is undefined, or where the first derivative is equal to, where the derivative is undefined. However, notice that if we look at g prime of t, which is equal to 1 over the quantity t plus 1 squared, our denominator is going to be 0 at t equals -1, so we don't have to worry about that spot because, again, it's not going to be in the domain. Our time is going to be positive or 0 up to whenever that time stops, so a negative number would not be in that domain. So again, we just have to focus on where the derivative is equal to 0 to figure out where the particle is stationary. So I set the derivative equal to 0. I multiply both sides by my denominator, so I get 0 is equal to 1. Right? This is a false statement. So there are no solutions. There are no spots where the derivative is going to be equal to 0. So we can say no. The particle is never stationary because g prime of t does not equal 0. And that would be an acceptable justification. All right, per usual, enjoy the rest of your day, and I will look forward to seeing you for our next video, where we will continue our discussion on particle motion.